It's hard to imagine that Earth is still in an ice age that stretches back almost 3 million years. And it was only 30,000 years ago that massive ice sheets gripped much of the northern hemisphere. They flowed south from the Arctic, across most of Europe. Actually, sheets doesn't even begin to describe the thick, humongous masses of ice that scoured and sculpted the landscape, grinding it down and carrying everything with them. "100 miles south of the edge of the ice sheets, near modern-day Sarlat, France, a different terrain existed. Here, evidence suggests Homo sapiens, modern humans, found a place to live, and they carved out an existence in a sustainable but still very challenging and cold environment. This human quest for survival ushered in the next great chapter in the story of Earth. From the ice sheets of Greenland to the bottom of lakes worldwide, geoscientists are extracting the story of Earth's past. These scientists know that if we are going to live here for generations to come, the more we learn, the more successful we'll be. Look up, look around, look deep below. On this episode of Faces of Earth, we see how Earth has shaped us and how we are now shaping Earth. Climate is weather that takes place over a long period of time, and Earth has seen a variety of climates. Over the last 900,000 years, there have been 8 or 9 advances and retreats of great ice sheets, shifting the world from warm to cold to warm again. There are no witnesses to the early chapters of Earth's climate story. But this doesn't mean there wasn't a historical record left behind. There was, and geoscientists are getting pretty good at reading it.
An archaeologist who wants to learn about past people will study the things they dropped. What did they leave behind? If you want to learn about the history of the climate, the weather, the atmosphere, you go to the things it dropped. What did it leave behind? And in Greenland, in Antarctica, and on mountain glaciers, there are these great piles of snow and ice, which is what the atmosphere left behind. It snows. And the snow falls and it piles up in layers, and there's a history of the world's climate written in these layers.
Every few years, for 4 months, central Greenland bustles with activity as scientific expeditions arrive from different parts of the world to drill ice cores out of its 2-mile-thick ice sheet. Dr. Richard Alley of Pennsylvania State University researches Earth's past climates and the dynamics of large ice sheets.
If you drill an ice core, you can actually look at it like tree rings, and it's summer and winter and summer and winter. And there's a huge number of stories that have come out of the ice cores. When snow turns to ice without melting, it traps bubbles. If you grab a handful of snow and squeeze, you'll break off the little spaces and there'll be bubbles inside. And nature squeezes by piling more snow on top, and it squeezes. And so there's this little bottling plant going on that's trapping old air and putting it in the ice sheet. And you can drill down, count down 10,000 years, break the bubbles, and you know what the atmosphere was. We also have many ways to estimate what the temperature was in Greenland in the past. We read that in some other things, and so we start telling a history. In Greenland, how snowy, how cold over time, how much dust was blowing in, how many cosmic rays were zapping the planet, how many little micrometeorites were falling, what was coming up from the ocean, how productive was the ocean. Meanwhile, you can go to Antarctica and ask, well, how much dust at the other end of the world? And you start to draw a net around the history of the planet, and you can read the climate.
At the National Ice Core Laboratory in Denver, Colorado, a record of Earth's climate is preserved in this collection of ice cores from the great ice sheets of Greenland, Antarctica, and mountain glaciers from around the world. The facility is kept at a constant 34 degrees below 0 Fahrenheit. Ice cores and their stories wait to be analyzed by teams of geoscientists. It's in the lab that the real work of interpreting ice cores begins.
99 at the bottom.
Each core is initially processed in the same way. Each step enables the story in the core to be read by different techniques. First, a bandsaw cuts a thin layer from the top of each core. This layer is then sliced into 1-inch pieces and sent out to scientists at a variety of institutions for chemical analysis. The remaining pieces are stored at the lab, waiting to fill requests from geoscientists around the world. The price per 1-inch sample? A cool $1,000. Next, the core's surface is plain smooth, kind of like polishing a window into the past. This is essential for the next step, measuring the electrical conductivity of each layer that ultimately characterizes the chemical properties of the core. Different climatic conditions over time are seen in different chemical signatures in the layers of ice. As 2 electrodes move down the ice core, 1,000 volts arc between them, measuring the fluctuating electrical resistance of each passing layer. More volcanic activity during a certain time means a layer would be more acidic, which is easier for the current to pass through, causing the readout to move upward. Drier or more arid times means less acid, and the reading shows a downward spike. Among other information, this is essential in dating each of the layers. The next stop is a preliminary analysis on a light table by a trained geoscientist.
This is a nice looking piece, actually. You got a lot of good crustings. A beautiful set of storms in here. Yeah, that's quite pretty.
It takes 90,000 years to grow a big ice sheet. And as it does, the world cools, the world gets dustier, the glaciers grind up the rocks and they wash it out front where the strong winds blow it away. And you see the record of this in the ice cores. You can see cooling into the ice age and warming out of the ice age and then into the next one and so on. We know that as the climate has changed, it's affected who lives where and what they do. So there's these records written in the ice core that say that climate really does matter to living things. You cannot ignore climate if you're alive.
Humans evolved in a world where ice sheets were more common than not. If you look back over the last million years, there have been ice sheets on North America and or Eurasia. 90% of the time we happen to be...
University of Virginia Professor Emeritus Bill Rudman has spent his entire career studying the overlap of climate change and human behavior.
For most of the existence of humans on this planet, we were reacting to climate change. Climate changed and we made do.
The human species originated in Africa and spread out into Eurasia. As climate changed through time, humans moved in response to the cooling and warming, spreading out and populating the world. We find signs everywhere of human populations in the finely wrought tools and points made of stone and bone they left behind. About 15,000 years ago, the great ice sheets began to retreat again. 2,000 years later, human survival became easier as the climate became more temperate as more and more areas warmed. Scientists have been able to tease out that these great changes in climate tend to happen in 20, 40, and 100,000 year cycles, begging the question, what is the driving force behind them? Just over 11,000 years ago, large changes in Earth's climate were underway. These were part of the same natural processes that had been going on for millions of years. Geoscientists have only recently recognized that these changes occur regularly, that climate has a rhythm.
One of the most important findings that climate scientists have come up with in the last several decades is that Earth's climate changes in cycles. And these cycles are driven by changes in Earth's orbit around the sun, not in changes in the strength of the sun, but changes in the orbit.
The shape of Earth's orbit varies every 100,000 years, from being nearly circular to being elliptical. Earth's rotational axis tilt varies every 41,000 years. Then, the direction that Earth's axis points toward the sun continues to change. It takes 21,000 years for it to point in the same direction again. When you add the effects of these together, Earth's climate changes at the same intensity the seasons change.
One thing that these changes in solar radiation drive is cycles of the ice ages, and the other is the cycles of the monsoons.
Monsoons are the heavy rainy seasons experienced throughout the world's tropical areas. In fact, over 50% of Earth's population live in areas affected by monsoons. Monsoons are influenced by the 21,000-year climate cycle, with rainfall increasing for 11,000 years, then decreasing again. This change can cause profound effects on the land, moving from temperate to desert and back again over the course of the cycle. But what if you want to know about the climate in a place where there was no ice 10,000 years ago? Like Earth's ice sheets, the thousands of freshwater lakes that dot the planet offer clues to the constant cycles of climate change. Every day, particles of dust and mud blown by wind or washed by rains collect in lakes. As these particles settle, they are trapped in the bottom as sediment layers.
Zero it up there, Eric.
In Duluth, Minnesota, there's an institute dedicated to studying large lakes all over the world. Here, Tom Johnson and Eric Brown are looking at sediment cores they've recently drilled from one of the oldest lakes on Earth, Lake Malawi in southeastern Africa. It dates back 4 to 5 million years.
Embedded in this relatively uniform-looking mud is an incredible history of climate variability. This core probably represents about 2,000 years, and we will nail that down precisely with both a combination of radiocarbon dating of the sediments and also by looking at the details of these laminations.
Much like the initial procedure with an ice core, the first step with the sediment core is to scan it.
Okay.
Tom and Eric use one of only 2 X-ray scanners in North America to examine the sediment core.
Yes.
This provides data about these cores that can be accessed by other scientists worldwide, minimizing the handling of these very fragile objects.
So what's first, Eric?
Because lake sediment provides a continuous record, scientists have discovered that every centimeter of this core represents a year of Earth's history. It will take the scanner several passes in the course of an hour to record its full length in a very highly detailed image.
So that measures the surface and that information.
Sediment cores provide not only climatological data, but also information about the plant and animal life both in and around the lake, all in resolutions or time frames down to a couple of months. Nearly 80 different elements are discovered in this sediment core.
That's iron, this is calcium, titanium, that's manganese.
In these African lakes, little changes in climate result in big changes in sediment composition. So as we look at this record coming out of Lake Malawi, we see these annual fluctuations in the amount of iron that's accumulating in the sediments, the amount of silicon accumulating in the sediments. We see this annual ringing of sediment composition.
You can see, how beautifully resolved the annual laminations are.
Look at the laminations on the X-radiograph, how beautifully they stand out.
This extraordinary scanner allows Tom and Derek to examine laminations or layers of sediment in the core a little thicker than a piece of paper. Previously, sediment cores could be dated in terms of decades. Now we can see things that represent months, which allows scientists to learn about seasonal conditions, among other things. A much more detailed picture of the entire region is now coming into focus.
The sub-Saharan region was unusually wet from 11,000 years ago to 5,000 years ago. And the record from Lake Malawi bears that out.
And we see in the human record that the climate evidence seen in Tom's sediment core is accurate. 11,000 years ago, man created these pictographs. Elephants, hippos, crocodiles. Life that thrived from a time when rainfall here was abundant. In the 1990s, NASA provided yet another window into this region's history. Low Earth orbit ground-penetrating radar made an amazing discovery. Lake beds and river channels now buried by today's desert. By 5,000 years ago, the monsoon cycle was shifting rapidly, and those long-lost lakes and rivers would have been almost dry. Early humans, on the move throughout history, once again needed to look for places where they could survive. This time, nomadic humans tried something new.
Some humans, for the first time, began to live settled lives. They lived in one place to be near their crops and also to be near their stores of grain. This changed people's lives. You were adding the agricultural produce to the hunting, gathering, fishing resources that were still available. So populations began to increase. What we think of as human culture came into existence, and it's pretty obviously tied in a variety of ways to the origin of agriculture.
Human survival has always been the result of our problem-solving ability. Agriculture was another in a long line of survival innovations, and it would have profound consequences for mankind's relationship with Earth. The Stone Age started 2.5 million years ago and lasted until 5,000 or 6,000 years ago. Almost everything in human history we call progress has happened in just the last few thousand years, truly in the blink of an eye.
We've assumed for the past 40 or 50 years that the present epoch is essentially flat line. There's no variability. We've learned over the past 20 years that there are very significant beeps, blips, and that they are of such magnitude that human societies really had to adapt to them, that we were not in control. We were responding to, adapting to abrupt, high magnitude, long duration climate changes.
For the past 30 years, Yale archaeologist Harvey Weiss has been studying the effects of climate change on ancient civilizations in the Middle East.
Here's the wall face, everybody.
Harvey and his team are working in northern Syria, excavating a site known as Talaylan, a 4,000-year-old fortified city, once part of history's oldest known empire, the Akkadian Empire.
This was a highly organized society that was functioning extremely efficiently. That is, rations distributed in liter-sized containers, of which we have measured approximately 10,000. Mass production of ration distribution vessels. They're sort of your favorite dentist Dixie cups, please gargle. And the big question has always been, what disrupted the Akkadian Empire, the world's first?
Here we are on the outsides of the Akkadian fortress. Here is an Akkadian floor with Akkadian refuse upon it, and everything above it for 2 meters is wind-blown deposits of different sized grains. Perhaps this deposit represents something on the order of 100 or 200 years of extremely different climatic conditions.
Harvey and his colleagues determined that, for reasons which remain a mystery, beginning around 2200 BC, rainfall in the Talaylan area abruptly decreased by 30%. This was no ordinary dry spell. It was a drought that lasted 300 years.
That 30% reduction in precipitation effectively wiped out cereal agriculture. That is, wheat and barley could no longer be produced in the region that had been imperialized. What we're doing right now is clearing the central courtyard of the central building of the Akkadian Imperial Palace. The large ashy deposit contains the artifacts left behind by the Akkadians when they abandoned this building.
One day, and perhaps it was literally in one day, Talaylan became a ghost town.
What we see in this photograph is the literal abandonment of the Akkadian Empire. Rooms with grain storage vessels, with clay tablets for recording the distribution of rations. All this is in situ in these rooms, and people literally walked away on this floor.
As their once fertile home faded into the distance, the Akkadians had no way of knowing there were others facing the same fate.
The same time, in Egypt similarly collapses synchronous with the Akkadian collapse. In the Indus Valley civilization synchronously collapses at 2200 BC. In the Aegean, synchronous early Bronze Age collapse. Across geographic regions, across cultural landscapes, across political landscapes, the same effect is observed. What the past 10 years of paleoclimate research has taught us is that the climate changes were of such abruptness, magnitude, and duration as for human societies not to be able to adapt to them except through collapse. That is, by moving away, by transforming themselves into lower energy consumption societies.
Some of Talaylan's inhabitants returned to a nomadic herding life. Others migrated south, joining with the people in the lands between the Tigris and Euphrates rivers, who were bringing water to their crops via irrigation.
We used to think we created civilization. We are the masters of our destiny. We control our fate. We are culture. And this forces a reconsideration of this on some very, very fundamental level. That is, how do natural forces push human societies to respond in certain ways, to adapt to very different and very abruptly different natural conditions? In very many respects, cultural evolution has been a product of natural environmental change.
Since the advent of agriculture, changes in the environment were no longer the only forces leaving a mark on our planet.
I'm standing out here in the southern Shenandoah Valley of Virginia, and if you look behind me, you'll see pastures and cornfields and forests. And to a city dweller, this is nature itself, but if you look at the landscape in a different way, it's all transformed. To grow a crop in a wooded area requires clearing the trees so that the sun can get to the soil. And people began to do it more rapidly when the bronze axes came in, and then 3,000 to 2,500 years ago when the iron axes came in. That transformation of nature is the largest change that humans have made to the face of the planet. We currently live in an interglacial climate, and there have been 3 or 4 of those in the past. This one is different. Beginning about 8,000 years ago, the carbon dioxide trend, which at times in the past that are most like today, was headed down and should have kept going down, went the wrong way, it went up. That's just about the time that humans began to clear forests. So my claim is that humans took control of the carbon dioxide trend all the way back 8,000 years ago by making it begin to slowly rise instead of fall.
Early civilizations rose and flourished. Moving past basic survival, humans began to investigate the world around them. They looked at ways to make life better. They invented, and they began to innovate with the materials they found around them. The technical abilities of the ancient Egyptians to work with rock and use the power and energy of the Nile to move vast quantities of material to build the pyramids are well known. But the Egyptians were not the only early civilized peoples harnessing the world around them. Not all rocks are for building stone monuments. Some hold metal ore. If you had metal, you had an edge. Humans made great leaps from the end of the last ice advance to 5,000 years ago. But as mankind figured out how to use the raw materials in Earth formed over billions of years, human development accelerated. Consider this: a mere 5,000 years lies between the first metal tools and the International Space Station. Early Roman technology left more than artifacts and splendid ruins. They also left a trace of their mastery of metal in a very unexpected place.
There's all these stories in the ice, and some of them do relate to us. Now, lead is out there naturally at very low levels, but humans use lead for lots of things. And when the Romans were building their plumbing, they used plumbum, which is lead. And they mined it, and that made dust, and a little of that dust showed up in the ice in Greenland. And you can see a little blip in lead from the Roman mining. And then the empire collapsed and the lead mining dropped, and it was cleaner for a while. And then the Industrial Revolution. We start using more lead for lots of things. And as we did, you see it rising in Greenland. And then we get to lead in gasoline. When you stomp on the accelerator, you don't want the engine to go ping, 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 so you put lead in. That burns, it's in the atmosphere. Huge rise in Greenland. And we said, hey, lead in great quantities is not good for us. Let's get rid of this. We'll go to no lead. We'll find something else to stop the knocking. Big fall in Greenland. And you can see us dirtying it up and us cleaning it up right there in the ice.
Yeah, there are. There's a few of them in here.
Humans have worked hard to improve our quality of life by being better at adapting to the world around us. The key is a powerful hedge: technology. Millions of years of Earth's geologic processes have left deposits of metal and minerals exposed on the surface where humans discovered them. Human imagination took the rocks, the metals and minerals stored in Earth, and shaped them with fire into plows, tools, weapons, even objects of adornment. And later, nails to build with, rails for trains, and even wire for telephones.
So we have a lot of development to do back here.
Early miners who tapped these resources were really the first geologists. They were perhaps the first people to find value in the rocks, extract it, and find ways to use it.
Wherever we've got an intersection of fractures.
At the San Javier copper mine outside Tucson, Arizona, geoscientist Mary Poulton teaches students how to read the clues Earth has left in the crust.
If you come in here, one of the things you notice is that we've got a really big fracture coming through here, and then we've got another one coming down here. You know, one of the neat things about a mine like this is that the structure controls so much of the mineralization, so you really have to puzzle the geology out in order to figure out where you're going to have good ore zones, and you have to get good at reading the rock.
Mary Poulton carries on the heritage of hard rock miners. Today, geologists continue to unravel the story of Earth as they search like super sleuths ever deeper and for more complex deposits of minerals to continue the advance of human civilization.
But it looks like it's pretty good copper in here. A lot of chrysocolla.
Pretty high-grade stuff.
Yeah, probably some silver in here as well. We have exponential demand curves for a lot of commodities. And frankly, we use a lot more elements in the periodic table today than we ever used to. From the 19th to the 20th century, we might have used large amounts of maybe 20 elements in the periodic table. Now we use them all. We say that if it can't be grown, it has to be mined. And so anything that's not a 100% organic source has to come from a mineral resource base. We're having a hard time keeping up with the demand. We found the easy deposits, and the deposits that we need to look for now are deeper. They're in more challenging geologic environments that we don't understand very well. They could be in politically difficult places for us to access.
Today, human progress is driven more by energy than minerals or agriculture. The material we use, the food we grow, are all dependent on the energy we can harness. And for humans right now, coal, oil, and natural gas power our progress in a manner that is both cheapest and most efficient to use. But in using fossil fuels, we release fossil solar energy stored as carbon over hundreds of millions of years. Releasing this ancient carbon continues what humans started at the dawn of civilization. But just as we have progressed since then, so has the evidence that we are making an impact.
Starting around 8,000, 7,000 years ago, we began to become a player in the climate system. So we entered a second phase. As natural processes were trying to cool climate, humans were injecting increasing amounts of these greenhouse gases. And in effect, I think that we canceled most of the natural cooling that would have occurred and arguably stopped the small beginnings of the next natural glacial cycle. As we get into the last 200 years, it's clear that humans have begun to dominate the impacts on the climate system. Nature still plays a role, but humans play a larger one.
Technological development is impossible to refuse. It makes life easier. Food is better and more abundant. It enables us to live longer, healthier, and fuller lives. There are now 6.6 billion of us, spread to all corners of the globe. Earth continues to evolve through time, but now we have become one of the forces of nature.
The extent of human transformation of the surface of the Earth is immense. If you look at Earth from space, very little of the area of the continents is in a natural condition. It's been altered, and that changes a number of things. There is one estimate that humans now, in the modern era, move more rock, soil, more debris around the surface of the Earth than all the effects of water and wind and ice combined. We're the major force transforming the surface of the Earth.
"4,000 years ago, people abandoned their homes in different regions of the world when Earth became unpredictable. Today, Earth's power and unpredictability remain, and humans can still find themselves in the way." Earth follows the laws of nature. It does not care about our property, our families, or our very lives. It goes about its business as it always has. But our increasingly technological society has made this fact easy to ignore. Many places where humans decide to live are also places where Earth's processes interact. What we experience as catastrophic events are just geologic blips in the ongoing evolution of our planet. Most of these events have only a regional impact. However, there are some that can have a profound global effect. When volcanoes erupt, microscopic particles explode into the sky in huge plumes of ash, steam, and hot gases. The ash and gas released from a volcanic eruption doesn't stay put. It's often forced so high into the atmosphere that it sweeps across the entire planet in a short time. In April 1815, over 1.5 million tons of ash blasted out of Mount Tambora near Indonesia. It was the largest eruption of modern times. The following year became known as the Year Without Summer. In Boston, it snowed in July. Across the United States and Europe, crops failed. A large eruption can lower temperatures for as long as 10 years. Our growing population will continue to be subject to Earth's activities. Some will be abrupt, like an earthquake or volcanic eruption. Others will be subtler and change more slowly, just as weather fades into climate. There's a lot of talk today about Earth's changing climate in surprising and alarming tones. The geologic record tells us that the climate has always cycled between cold and warm. These conditions are natural to the planet. But the geologic record also reveals that we should be in a cooling cycle, but we're not.
"200 years ago, thereabouts, the industrial era began, and the technological innovations have piled one on top of the other and taken humanity to a very different place from where it had been for the thousands of years prior to that. We're clearing forests more rapidly. We're burning fossil fuels for the first time in abundance, and both of those processes have put enormous amounts of carbon dioxide in the atmosphere.
Science isn't just about understanding the processes that govern our planet. Geoscientists are beginning to grapple with solutions to the problems we face as our relationship with our planet continues to change and will for generations to come.
The ship's crew on duty up there are going to have you taking turns steering the ship on course.
Today, Tom Johnson of the Large Lakes Observatory and a select group of graduate students, hopeful future geoscientists, are continuing an ongoing research project on Lake Superior.
Team number 2 are going to be doing the tri-axis, which means...
Lake Superior is the largest freshwater lake in the world in terms of surface area, which makes it a phenomenal laboratory for study. By virtue of its size, it creates an oceanic climate. The Blue Heron is a research vessel owned by the Large Lakes Observatory. A variety of instruments will be deployed to compile a comprehensive picture from the surface all the way to the bottom. The Tri-Axis is a critical part of Johnson's technological arsenal. Today, this remotely controlled navigatable robot is configured to measure the presence of several organic compounds, key indicators in determining the health of Lake Superior. Precise temperature readings will also be taken at various depths. These readings and the Tri-Axis data will be transmitted in real time to computers below deck, where they will be analyzed and monitored.
It looks like about 17.8 degrees at the surface here.
These measurements will be repeated on several different parts of Lake Superior over the course of this
So
voyage.
hitting the joystick should just mean...
Lake Superior is also the deepest and coldest of the 5 Great Lakes. However, years of recorded temperature data is now telling geoscientists that the lake is warming faster than its surrounding climate.
Reach out there and stabilize that thing so it doesn't swing.
Lake Superior freezes over once every 20 years. If this warming trend continues, scientists estimate that by 2040, it could be completely ice-free in the wintertime.
We have something like 25 years worth of temperature data. And it turns out that this year is the second warmest year on record. 1998 was the hottest year. 2006 is the second hottest year. 2005 is the third hottest year on record. So in the last 8 years, we've had certainly the 3 hottest years since we've been measuring temperatures in Lake Superior. I mean, in some ways we love it. We can finally swim off the rocks of Duluth in this part of the lake. But in other ways, it is a matter of concern. It's going to have a tremendous impact on the biology. There will be changes in this lake.
Humans are now in the driver's seat, and we have to change direction. It's possible, but we have not really taken on the challenge yet in a global scale that we're going to have to.
Jeffrey Sachs of Columbia University is in the forefront of sustainable development.
We're intervening in more of the Earth's processes and to a point of danger for human society. We're realizing that we have these limits that need to be obeyed. That doesn't mean a limit of human ingenuity, science, and technology. It doesn't mean a limit to our ability to improve the human condition. Not to give up on progress, but it is to understand that progress has to be in harmony with the physical Earth. So the 21st century has to be the century of sustainability.
Earth continues on through time, changing constantly. Humans have succeeded here because we are adaptable. But as we advance in our abilities, it would be a mistake to think that we stand on equal terms with our planet. Until recently, humans viewed Earth as an endless resource for our development. From agriculture, minerals, and energy, our focus has been on how to harness the next oil field, or coal mine, or forest. After all, it seemed that we could always find more resources. Today we are realizing that the world is a much smaller place than our ancestors thought. Our future development depends on renewed ingenuity in living with the world around us. Earth keeps time in a different way and on a different scale than we do. But through a better understanding of how our planet works and our relationship to it, the human journey will continue on a destiny inextricably tied to this planet and continue to walk across the many different faces of Earth.